So good evening or good morning, both. Anyway, so we'll start the evening session. The first speaker will be Professor Ariando from National University, Singapore, talking about the infinite layer nickelate. So Ariando, please take us away.
All right, thanks everyone, especially the organizers. Yes, good morning, good afternoon, good night, everywhere you are. So I changed my title slightly, so I'm today just focusing on the effects of these oxygen reductions during this calcium hydride superconductic process on the superconductivity and the nickel 3D orbitals in the infinite layer nickelates. So, well, this work mostly done by my former group members, Sengwei Zheng and Chisin Tang, as well as, of course, with the help of many other people in our group and at different institutions, as you can see here. Also, I'd like to thank the funding agency, first of all, the National Research Foundation of Singapore, Ministry of Education, and Agency for Science and Technology and Research, Singapore. So I believe this group of audience do not need any introductions on these motivations of the infinite layer of superconductivity. But in any case, let me just give a brief overview again. So to try to understand the different competing orders that we have in couplets leading to the high TC superconductivity. So we have been talking a lot about trying to find an analog system and nickelate somehow with this square planar lattice like at the nickel 1 plus state. So this can replicate the 3D9 electronic structures of the couplet with this lifted orbital degeneracy, hopefully the single orbital half filling as well. And yeah, so this is something that we have been looking at in the last maybe 20 years. And yeah, as we know that we have seen all of the different new discoveries on superconductivity in this nickelate. So to achieve this 3D, of course, we can start with a different type of compounds, basically the RP phase with different layers. So the infinite layers will have the 3D9 when you can reach the nickel 1 plus. So this by hole doping, we can expect that we can have the 3D electron count comparable to what we have in the superconducting dome of the couplet. So as well as the 5 layer, for example. So this will give you directly after you remove the apical oxygen to the same 3D or comparable 3D electron count in this dome of the couplet. Right. So at least now we have seen 3 different families. So the infinite layer, the kind of well-established one, because we have a different types that I can briefly show later on, our family. So the 5 layer one was also shown to be superconducting in 2022. And recently this the perovskite versions of the bilayer under high pressure also showed these transitions as well as in the resistivity as well as in the susceptibility. Nevertheless, as we can see, there is still a big challenge, especially with the finite layer, the 5 layer, and the this bulk perovskite with high pressure. So it's very limited information that we have so far. So the infinite layer, since the discovery by Harold's group, so we have seen a lot of progresses. And this is what I'm trying to focus on today. So looking into the electronic structures of the infinite layer, we all know that having these apical oxygens removed, So we can expect that there is this 3dxy square minus y square orbital lifted and isolated somehow because of the square planar crystal fields that we have. So recent couple of results also have indicated that the electronic structures represents more of the Mott-Hubbard band, Mott-Hubbard picture rather than the charge transfers we have in the couplets, with the charge transfer energy likely much larger than the Coulomb repulsion's energy. And on top of this one, there is also discussions about hybridizations of the 5D with the 3D orbitals, leading to, in the fermiology of this infinite layer nickelate, that you also have these two pockets of electrons, the dxy and the dz square, at the center of this Fermi these band structures. So with the hold up pictures, hold up pocket at the dxy minus y square. So there have been a number of versions of these infinite layers, and the most recent one is this ND ytterbium nickel oxide by Charles Hans, where the reductions also done a bit different in terms of apical oxygens, which is through the capping of the aluminum layer. So they all shows kind of comparable in terms of the superconducting dome, as well as the basic macroscopic electrical and magnetic properties. So for example, in comparisons to the cuprate, the underdope or the overdope, instead of the insulating state, we have mostly this weakly insulating, so it's still showing some kind of conductivity. And there is also a change in terms of the dominant carriers at the normal state from the hole to electrons as you cross for the doping or as you go lower in temperature. So there have been also many other reports in terms of basic properties like the critical field, SC1, SC2, coherence length, pairing symmetry, rotational symmetry, features of this in the plane of the infinite layer, as well as the nature of the dimensionality. So this is some of the report coming from ourselves. The need for the confirmations that, for example, in the case of the dimensionality, it is not very close. It is still not it's not similar to what we have in the cuprate. So there is kind of effect of the fluctuations of the cations that can be used to choose the dimensionality from quasi 2D to more 2D or even to 3D nature. So we have been working also on this, but still a work in progress, and we hope to also make more convincing result out of this direction soon. So the other things like the competing orders, so the report on the charge orders, charge density wave, and as we just mentioned just now, that there was a new report about the absence of this charge order by Carlsen's groups. So, and yes, of course, other things like the strange metal state. So the point is there are many similarities, important similarities, but clearly there are also very strong differences between the cuprate and the nickelate. And so this is, so before we even going further with this, right, I think it is really important to try to understand the origin of this one and to overcome these issues, so that we can really come up with a conclusive results in terms of what states that we have in the nickelate and in comparison to the cuprates. So I'm trying to argue today based on the point of that we are unable to really produce pure infinite layer phase. So all of the effect that we are seeing might be or can be related or can be due to this non-pure infinite layer phase. So there is appearance of RP phase, secondary phase defects. So even during the growth, initial growth of the perovskite, and worse than when we are doing the oxygen reductions by calcium hydride, for example, there has been also many other effects, formations of defects on the surface or absorptions of the oxygens, formation of other secondary phase, or even the intercalations of this hydrogen. So in view of the hydrogen intercalation in this infinite layer structure after the reductions by the calcium hydride, help from Vienna reported, I think also in by another group, I forgot to include it here, that both possibilities that having hydrogen intercalated in the structures during the calcium hydride reduction, as well as the pure infinite layer phase, energetically favorable, but they might slightly different that, and also lead to a different kind of the orbital rearrangement of the 3D structures. For example, if you hope to if you manage to have a infinite layer phase, so your 3D9 structures can really isolate it in terms of the 3dxy minus y square with at the undoped case with slightly electron drop by the implications of the 5D. On the other hand, when you have this hydrogen intercalated, so you likely to will end at the insulating state, so the 3D mode insulator, where the dxy minus y square.
Hi, all in the audience. Could you mute yourselves, please?
Kind of come closer to each other, right? And there is no 5D pocket. All right, so let's move on. So that's from the theoretical point of view, and we have seen a report on by time of flight secondary ion mass spectroscopy detecting that there is this large, relatively higher intensity of the hydrogen to the base case. For example, the reduced SCO or the perovskite and NSO before the reduction. So you can see the report indicates that there is this large, higher intensity of the hydrogen detected in the structures. And by calibrations, they try to correlate this with the concentrations of the hydrogens in the system. And they argue that when you have the hydrogen between somewhere 0.23 to 0.28, if I'm not mistaken. So this is the state where you have the highest TC, the optimally doped case. On the other hand, the observations of superconductivity by using this aluminum capping would likely involve much less hydrogen. So this indicate the opposite case, as well as the report by Hepting before groups by Purple. So a couple of study on the bark crystal lanthanum nickel oxide by neutron scattering indicate that the majority of the excess hydrogen reside likely in the secondary phase or in the defect state of the samples. So it has been quite a challenge to try to produce very high quality of the pure infinite layer phase. So we have been working also on this separately with different in situ monitoring and so on. So the two state, the initial growth and the reduction phase, to us looks like they are equally important and independently. So it doesn't matter whether you get a very good phase in the initial growth of the perovskite or not. If you did somehow the reductions using not an optimized parameters, you will also end up with the non-pure phase and non-superconducting states. So the same if you have a very good phase in the initial growth, the perovskite phase, with a very less, let's say, secondary phase, then if you don't do a proper reduction, so you can also end up with a secondary phase after the reductions. So both have to be optimized, and especially in the case of the reductions, it seems there is a very clear window of where you can produce highly pure infinite layer phase. In terms of the initial growth, we have not been able to produce more than 5 to 6 nanometer thickness to be able to produce pure phase after the reductions. So the initial growth, so the thickness that you can achieve, can use to achieve a very high pure infinite layer phase has to be around 6 or below 6 nanometer. Plus, after reductions, capping is important. So without capping, even if you have a very thin layer, so there will be formations of defect phase or secondary phase after the reductions. So thickness still have to be limited. First one. The second one, the capping layer has to be used to be able to maintain this as high as possible pure phase that you want to have in your films. So at least this is what we have concluded so far. And then based on this one, we try to do a comparison study in terms of the effect of these reductions using 2 different state of samples. So the first one is this thick, thin, less than 6 nanometer and capped with the STO layer. And the second one is the thick NSNO, so ultimately doped, presumably in this case 20 nanometer without capping. And this, as you can see also from this XRD, the infinite layer 5 nanometer capped with STO shows a very, before you can also see almost no obvious defects in the stem image. So here you can also see that there is a nice lower oscillations in the XRD and showing the infinite layer peak clearly shifted. And then at higher reduction time, again, shifted to the left indicating that there is also a slight change in the lattice constant of the z-axis as you reduce or as you over reduce your system. On the other hand, the thick NSNO shows much less quality, and we are sure that at the top layer, the system full of secondary phase or RP stacking fault, and after reductions, likely there is surface reductions in quality and absorptions of some oxygens. So the resistivity showing that when you under reduce, so there is still metal insulator transitions. So at the optimally reduced around 180 minutes, in this case 360 minutes. So you have a very nice transitions with a TC0 around 10 Kelvin. And then as you over reduce your samples, the system become showing the metal insulator transitions again. So the same in the case of the resistivity also decreases as you increase the reduction time from the under reduced to optimally reduced. So this is for the thick samples. We can achieve superconductivity at around the same time. And then as you reduce further, you can see the increase, the appearance of the metal insulator transitions again. All right, so using these two samples, we do the comparison study in terms of the time of flight secondary ion mass spectroscopy. So this is the hydrogen intensity showing the negligible effect, negligible enhancement in terms of intensity with respect to, for example, the STO or the S-grown, the perovskite phase for the case of the for these thin film samples with a capping STO. So the bottom one also show the expected nickel, titanium, and Nd ions as a functions of sputtering time or the depth, as well as you can see on the right is the 3D mapping of all of these elements. Okay, let me move on a little bit fast. So this is comparison to the thick samples. As you can see, in the case of the thick sample without capping, there is a large increase of the hydrogen. So at the surface, both of them show, of course, always higher intensity. But as you can see, as you go deeper into the NSNO, in the case of the thick samples without capping, it's clearly showing larger intensity in comparison to the thin samples. So this is just a comparison for the other atoms, so not very important to discuss right now. So there is also, if we look to the resistivity, there is also a change in the Hall coefficients as you go from the, in the case of over reduced or under reduced. So the system remain electron-like system, while when you have the optimally doped, there is a crossover to of the Hall coefficients at low temperature. So this indicates there is a multi-band nature, as we point out before, in the case of this infinite layer nickelate, which might be of interest to look into as a function of the reduction time of the oxygen. So that's what we did. So we did X-ray absorptions, linear dichorisms, looking into out of plane and in plane, using out of plane and in plane polarizations. as a function of reduction time. So as you can see, the two peaks is the transitions from the P to 3D, L3 and L2. For in plane, so in plane is much larger than the out of plane. And we look into the difference of this in plane and out of plane. And then here showing the difference as a function of the reduction time. So as you can see, there is an increase in the asymmetry of the absorption as you increase the reduction time, and then it decrease again. So to summarize this, we can look at this phase diagram. So the x-axis is the reduction time. So the TC is plot on the right side, as you can see before from the resistivity that we can divide this into three regimes: under reduced, optimally reduced, and then over reduced. So on the same plot, we can plot the asymmetry of the absorptions between the in-plane and out-of-plane incoming photons. And this show the similar trend as you increase the reduction time. So we can conclude from this that there is this increase in the separations because of the asymmetry between the out-of-plane and in-plane. So the optimally reduced system likely much more isolated in terms of the dxy minus y square, while in the case of under-reduced and over-reduced, possibly the 3D z square lifted closer to the dxy minus y square. So this make this become the absorption more symmetric. So just to conclude, so we shown that there is a negligible effect of the hydrogen intercalation in the case of a pure infinite layer phase. So likely the hydrogen easily reside at the, or prominently reside at the defect state or the secondary phase of your infinite layer nickelate. So the optimum reduction is seems very critical, in particular to obtain this isolated 3dxy square minus y square orbitals, and thus the superconductivity. So with this, thank you for your attention.
Okay, thank you very much. Thanks for the very nice talk. This is open for a few short questions or discussions. Let's see, I'm mixing clapping and hand raising. Let me see, Yonghun, please go ahead.
Oh, yeah. Well, thank you for the nice talk. So I just had a quick question about the TEM image that you showed. It seems like the bottom interface seems very clean, but the interface between the film and then the cap seems have some, yeah. So I was wondering if you could give me a comment about why the top interface looked like that.
So I'm not sure whether this is more because of the scanning of the, or is it really the at the boundary where we start to have a, maybe I can ask my STEM guy if he is here. Joyang, are you here? Could you comment on this one?
Yeah, I'm here. Actually, this is due to the energy of the STO growth. So when we grow this sample, STO energy set so high. So actually one layer of the nickelate has been penetrated by the STO. So that's why we can see one layer or two unit cell RP phase in the top, on top. So I think it's fine.
Okay. All right. Yeah. Thank you very much.
Okay. Maybe a quick one from Bai.
Yep. Hi, Professor Ariando. Very nice talk. I have a question regarding the near the end when you discuss the optimal reduction, and if you're away, you will have additional complications from the DZ squared. Can I understand that just from the doping induced by the oxygen off stoichiometry, or there's a different mechanism?
For the overreduced, likely, I mean, of course, this is just hypothesis from us that the oxygen vacancies might be formed,
Okay.
and that can also be seen from the lattice constant, which increased slightly, and change the nickel oxygen order, distorted, that might leave this DZ square. So in the case of the under-reduced, yeah, the apical oxygen for sure still there, partially. So this might also affect the DZ square orbitals to be lifted up.
I see. Thank you very much.
Okay. Actually, let me do something strange. When we began before, Peng Cheng had asked about this current status of XX oxygen and stripes. It's kind of related to Ariando's work. Do you mind if I solicit Kyle's comments? Because he's done some very extensive and nice work on that recently. Kyle Shen.
Yeah.
So.
Yes.
It's Kyle's paper, right? I saw.
Yeah. Well, so Kyle, if you're free, do you want to chime in, please?
Yeah, I mean, so I guess I'll just kind of very quickly just summarize what we found. So I should say that it's restricted just to the neodymium nickelate. So we haven't, I think as Harold alluded to, we haven't looked at the lanthanum nickelate, but certainly in the neodymium nickelate, what we found is that when you reduce the perovskite from neodymium nickel 3 and neodymium nickel 2, it doesn't progress, directly, but there's basically it progresses through the formation of a brown millerite-like phase, which has 1/3 of the apical oxygens filled. And this has actually been first established by John Mitchell's group. So they did some in situ reductions of bulk neodymium nickel 3 and found that this occurred. And so we basically found the same thing. And so what you see is that the strength of the signal from this brown millwright-like phase is extremely strong. So you can even, you can see it on resonance, but you can actually see it off resonance. It's about 2 orders of magnitude stronger than what one would see in something like a cuprate or something intrinsic. And so what we could basically concluded is that at least in the case of neodymium nickel 2, you can you only need a very, very minute amount of this impurity phase, about something on the order of a fraction of a percent, to give the kind of signals that that we had seen in some of our ostensibly neodymium nickel 2 samples and what other people have reported as well. I think there's still a little more work to be done to see whether or not that's true for lanthanum nickelate. As Harold has pointed out, no one has reported yet, these 337 or 338 brown millerite phases in those compounds. I think we need to maybe do a little more work to see if that's indeed the case there, or if it's something different.
So did you also look at the thickness dependent?
No, all of our samples were basically the same thickness. We had samples that were all the same thickness, the same capping layer thickness as well. And we just used different reducing conditions. And so if you reduce it more lightly, you get things that are, 3.3, almost all 3.37 or 3.38. And if you reduce it fully, basically this signal completely disappears.
Mm-hmm. And the thickness, remind me again?
These are 20 unit cells.
Right. Okay.
Okay. Actually, forgive me. I thought, Izzy, do you have a question? Or is this from responding on the microscopy side? I assume that was with respect to the microscopy side. So, Well, I'm very interested in this, but in the interest of remotely keeping schedule, maybe we should move on. So thank you again, Ariando, for a great talk.